evening, everyone. I am Saptarshi De. I am a PhD scholar at Electrical Engineering Department of IIT Bombay. And welcome to this fifth doubt clearing session for the NPTEL course of Electrical Machines 1. And as you know that these doubt clearing classes are held thrice a week by three of us, and I take the doubt clearing classes on every Saturday, 7 to 8 p.m. So, okay, so this is the fifth week, and the fifth week lectures mostly cover three-phase transformers, different topics of three-phase transformers like their connections. You can change the connection of three-phase transformer to achieve different vector groupings, and corresponding phasor diagrams you can draw. And there is one kind of unbalanced, not unbalanced loading, one kind of fault tolerant loading you can say of three-phase transformer, that is open delta connection. And lastly, that was taught was current and flux harmonics in transformers in case of saturation. So before we start, what I usually do every week is I take a poll of how many of you have watched some or all of the videos of this week 5. So could you please raise hand if you have watched some or all of the videos of week 5? This is not a part of your evaluation. So I just for me to know where you stand with respect to these study materials. There are only 6 students, I think. Someone left after I asked. Well, then we will, in that case, summarize a bit what was taught in this lecture. What I always say that these doubt clearing classes are not substitutes. These are supplements to the actual classes that are, the actual classes means the lectures that are uploaded on NPTEL website. These are only doubt clearing classes, not the substitutes, supplements to them. Okay, so three-phase transformers, actually all the transformers that you see here in our locality are all three-phase transformers. As you know that power generation, distribution and transmission are done in three-phase lines. So we require three-phase transformers for stepping up and down or for coupling between sectors of transmission lines. So all the transformers are three-phase mostly. Single-phase transformers are used in other cases like welding or some other application, or if someone individually installs a transformer. But mostly transformers, large transformers are always three-phase. Now, three-phase transformers can be can be realized in two ways. You can have proper connection of single-phase transformers. So 3 single-phase transformers you take and separate units. Okay, so separate as 3 separate transformers. Say they are like this, and they are coming with their leads, input-output leads, with dot conventions painted on them. Dot convention we discussed last day, and depending on the dot conventions you connect them so as to get your required three-phase connection from these transformers. On the other hand, this whole thing come as one single unit. So actually, performance wise, unless there is a fault or something or some other special issues, performance wise these two things are the same. Because if you look inside a single unit of a three-phase transformer, you will basically see the same thing. 3 sets of primary and secondary windings. Say you have limbs like this. names like this and say the primary and secondary of one phase is connected here, other one is connected here, and the other one is connected here, something like this. So operation and performance wise, they are more or less same, except for some special, not special, faulty cases, some problem happens. Okay. Now, as you know that when you have three windings, there are two ways of connections. You can connect them in star, that is the primary of the transformers you can connect in star, or you can connect them in delta. Similarly, the secondaries also you can connect them the same way. So in this fashion, there are several possible ways of connection of three single phase units of transformers so as to realize three phase transformers. Now, you might think that, okay, so in primary I have two possibilities, star or delta. In secondary I have two possibilities, star or delta. So in total I have four possibilities of connection in three phase transformer. But only the connection is not the thing here. Another thing is the phase. In what phase they are connected. That is where the topic of phase grouping comes here. So if we quickly draw, say I have three transformers, single phase, separate single phase, identical transformers. So how I will draw is, on the left side I will draw the primaries, on the right side I will draw secondaries. Okay. And this thing I will also copy so that we can talk about them later once again. I will keep it somewhere here. We will see. So I have this. Now, you see here, the dot convention is important. We will see. Without dot convention, you cannot connect transformers. Say the dot convention is like this. The dot convention comes painted on the transformer, okay? Or else you can do polarity test so as to find out the dot convention. Now, this is the primary and this is the secondary. Suppose at first we want to connect them in YY, that is both of them will be star. So, the primary supply comes from here, okay? I am writing AS, BS, CS means supply voltages like this. Now, so if I want star connection is easy. Simply create the star point. Short circuit all the windings at one side and you get a star connection here. Now, on the other hand, the question is which points to short circuit, this or this? We will see what will happen if we short circuit the other ends and what is the difference between them. So let us name them A1, A2, B1, B2, C1, C2. These are the primary and lower hand letters are secondary. Okay. So if you have any doubt, you feel free to interrupt me at any time and ask questions. And here also I create the other short circuit. So my loads are connected here. These three leads go to the loads. Now we will draw phasors. Okay. So what happens here is, you see, this AS, PS, CS is three phase balanced supply, right? And A2, B2, C2 are shorted. So let us say ABC is our phase sequence. Now if I draw the phasor, so this is the thing. So it is 120 degree shifted. This is the neutral point. Neutral point means A2, B2, C2. They are shorted here. Now I said that phase sequence is ABC. Now can you tell me where should I write B1? Should it be here, B1 or here? Right or left?
Right, sir.
B1 will be right, considering that phase sequence is ABC, and our convention says that phasors rotate in anti-clockwise direction. If you take the other convention, clockwise direction, then it will be the other way. Okay. So if B1 is there, C1 is this. Now how to draw the secondary phasors? Secondary phasor I will draw with some other color, say red. Okay, so first we will see how the secondary phasors will look. See, when you have an ideal transformer like this, and with this kind of dot convention, so if you take E1 as this, see, notice the polarity of E1, okay? Oh, E1 as this, so this is the polarity I am taking, plus, minus. This was dot, this was dot. So again, if I take E2 polarity as this, then E1 and E2 will be in phase. Okay. Now you see here, A1 has the dot, and here also small A1 has the dot. So A1 in the secondary side, this will be A1, A2. Why like this? Because parallel to this, they are in phase. So in this direction. Similarly, B2, B1, and C2, C1. They will be like this. Now the question is, they are shorted somewhere. So how to draw them together? See here, A2, B2, C2 are not shorted. A1, B1, and C1 are shorted. Right? A1, B1, and C1 are shorted. So what I have to do is, let us first draw A1, phase A, A1, A2. Now I will draw B. Now see, B is here. What we can do is, we can shift them parallelly to each other. So I have to short A1 with B1. So I will shift B parallelly here, so that I get B1 here. So I have B1 here and B2 here. Similarly, I will shift C parallelly here. See, B1, B2 line and B1, B2 line, they are parallel to each other. What I drew initially. Again, sorry. Although the lengths do not match, please don't worry, the lengths should be the same. Okay, I am just shifting them parallelly. So this is C1, C2. So this is the phasor diagram. Now, if I look at it, this phasor diagram, see, in the first phasor diagram, we had this A1 pointed upwards in this direction, while in the secondary, it is pointed downward. It is pointed downward. So, you know, if you consider, just a second, let me make space here. A wall clock. Think about a wall clock. Sorry. So in the wall clock, you have 12 here, 6 here, 3, and 9 here. And you have 1, 2, 4, 5, 7, 8, 10, 11. So you see here, the primary is this. You always keep the primary as your reference, okay, while trying to understand the phase grouping of transformers. So the primary, just a second, where did it go? Yeah, so the primary is here at the 12, and this was the primary A, and the secondary A, you see, it was downwards here. So this is the secondary A. Oh, I should have drawn primary with green, right? I will draw it with green. The primary is here, primary A1, and the secondary A1 is downward. So the secondary is looking at 6 o'clock, 6. So this is called capital Y, small y, 6. So if you have 3 transformers, single phase transformers with this kind of dot convention, and just by looking at this connection, if you connect them in this fashion, what the connection that you get is called YY6. Now the question is, why so much pain to take? Like you can understand, okay, now we will use this. You can ask that what we did here is we connected these 3, right? Well, I should have copied them also. Okay, anyway, A1, A2, B1, C2. So this is A1, this is A2, this is A1, this is A2. What we did is, say the primary connection I am not changing, one change at a time. I am not changing. So instead of shorting these 3, what we did last time, we could have shorted the other parts also. We could have shorted this also, and we could have given this leads to the load. How would it change anything? It would change nothing. From the load point of view, it would change nothing. The load would still see the same voltage, same current. The load doesn't care how the primary voltage is. What is the phase? Not the voltage, the phase. So why is this kind of phase grouping and their nomenclature is important? That is, you will mostly know about it in the next lecture. I will just give you some idea why it is important. Suppose this thing we talked in the last lecture also, that you have already a 3-phase transformer installed in your locality. Okay. And there is an increased load, so you need another 3-phase transformer. Now, when you are, so basically those 2 transformers will operate in parallel. Now, when you are doing parallel operation of transformers, they must be from the same phasor group. Why? We will see. We will see why. So that is A1, A2, B1, B2, C1, C2. Okay, dots here, dots here, dots here, dots here, dots here. Okay, let me copy paste this once again so that, sorry. So the question is, instead of connecting those terminals, instead of connecting these terminals, what if we connect or short these terminals? Primary, we are keeping the same. Primary, we are keeping the same. If you draw the phasor diagrams in the same fashion I showed you, you will see the primary will be like this: A1, B1, C1, whereas the secondary will also be like this: A1, B1, C1. So what do you have here? You have Y, Y0. Y, Y0. That is, here if I draw this clock once again, if I draw this clock once again, the primary is our reference, so it is always pointing at 12. The secondary is now also pointing at 12. So there is no phase difference in between them. The secondary is now also pointing at 12, A1. Now, if the previous transformer that was operating in that area was this, sorry, capital Y, Y6, the other transformer that is going to be installed also has to be the same, YY6. It cannot be YY0. Why not? What will happen? Because the secondary voltage was previously having a phasor like this. Having a phasor like this. This was 0, this was something. Now on this, if you connect another transformer which has phasors like this, basically you are short circuiting between two AC sources. Now AC source, when you have DC source, suppose you have one DC source, say ideal DC source, let us say. Okay, perfectly ideal DC source, and their voltage is also perfectly match. 10 volt, 10 volt. Say like this. You can connect them without any harm. There will be no current flowing through it. Even if I connect a if I consider small series resistances also, if the voltage is exactly match, then there is no current flowing through this. But for an AC source, you cannot connect them in parallel if you sure only about the voltage. Say you are sure that this is also 230 volt RMS, this is also 230 volt RMS, perfectly matching, then also you cannot connect them until and unless you are also sure about the phase. Because say this is voltage 1, V1 is say 230 sine omega t, and say V2, I should write root 2, I said RMS sine say omega t plus some phase angle phi. So what is happening here is, so if you connect one AC voltmeter here, that will be 230, another AC voltmeter, that will also be 230, but that is the RMS. Their instantaneous values are not matching. So if you have a small impedance here, that difference in instantaneous voltage, that will create a large short circuit current. So if I draw the graphs, so if you have one voltage like this, 230, its peak will be around 325 or something, and if you have another voltage which is also 230, another voltage also 230 volt, only a phase lag is there, phi. But instant to instant, if you see, they are all only for this instant and this instant, except for these two, they are always different. So there is a large current flowing. So when you are paralleling transformers, you have to make sure that not only their magnitude is same, not only the magnitude of voltage is same, but also the phase should be same. Then only you can connect two transformers in parallel. That is why these phase groupings are important. If you are using one single transformer, it doesn't matter whether you are connecting it in YY0, YY6, it doesn't matter. But if you are connecting in parallel, it matters. Okay. So any question about this phase grouping and transformer connection? No, everyone understood everything? Okay, then someone unmuted. Any question? No? Okay. So that is star connection we discussed. Now similarly star delta also. We will see one, okay, let us do the other way around. Let us do delta star. Why delta star? Why is delta star important? The transformer that you see in your locality on the poles, all of them are delta star. The 11 kV line that comes to your locality, that goes to the delta primary of the transformer, and the secondary is star. So this is the neutral is grounded. This neutral is nothing but the neutral wire that comes to your house, and different house gets different phase. Some get phase from here, some gets from here. some gets from here. The distribution companies try to balance the load, although it is not possible to balance it completely, but they try to balance it as much as it is possible. So you might see that sometime it happens that at your locality, some of the houses are facing power cut. So your house is facing power cut, but other houses are having the power. That is because one phase goes, the other is there. Okay, you can also notice that when such things happen, only a group of houses is always out of power. Only a group of house is always dark because they are connected to the same phase. That same group is always. Okay, anyway. So that is why delta star I thought I will discuss. So delta star. I will quickly copy this thing. All right. So delta connection, basically what happens is ending of one goes to the beginning of the other. So if this is A1, this is A2, this has to be B1. So ending of one goes to the other. So let us connect it this way. A2 goes to B1. A2 goes to B1. So B2 will go to C1. And C2 will go to A1. And some point will receive the power. Let us say this point receives the supply. So say this is the supply voltage A. This is the B. And this receives the supply voltage C. AS, PS, CS. On the other hand, secondary side will short. This is the delta star combination of connection for transformers. Although the transformer that I just gave you an example of, those are not three separate transformers. Those are one unit only. But one unit doesn't mean that they will not have dot convention. There will be dot convention. There will be connections like this inside the tank. Only this neutral and this connections will be brought out. Other connections will be inside the tank. Okay. So it is in delta. So definitely it will look something like this. The phasor diagram would look something like this. Okay. So let us say this is A1, A2. Okay. So A2 to A1 is in this fashion. Now we have a phase sequence of ABC. So can you tell me which one will be the so I have the other phases like this one here and the other one here. So I have two more arms left, 1 and 2. So between 1 and 2, which will be B phase? Can you tell me? 1 or 2? Should it be
sir.
2? No, you see, when I am saying it's ABC, it means that B lags A by 120 degree. So if I do it, increase it this fashion, extrapolate, then this is 120 degree, right? This is an equilateral triangle. This is 60 degree. So A is here, B lags A by 120. So it's 1, this arm 1 is B. And the other one will be C, it is leading A. Okay, I will erase this so as to make it less clumsy. Okay. So it will be is connected to B1. No, just a minute. I think you were correct. See, A2 is connected to B1, right? But what about the
A2
phase?
connected to B1, sir.
A2 is connected to B1, but what about the phase? Okay, so basically what happens is, although we have a phase sequence of ABC, a connection of this fashion is actually changing the phase sequence in these coils, but that doesn't matter. That doesn't matter in the operation. So A2 is connected to B1. So you are correct, yes, B1 will be here, and B2 is connected to C1. So C will be like this. Now how to draw the phasors of the secondary side? I will take blue. Okay, first we will draw them separately. So A2, A1, we have B1, B2, and we have C2, C1, right? We have this. How do we have this? Because they will be in phase with their primaries. So I have drawn them in parallel with them. Okay? So this is small c. Okay? Now we have to draw them so that their star connection is understood from here. So A1, P1, C1 are connected. So I am drawing A once again, parallel to this. A1, A2. B1 will come here.
Sir, without the rearranging, we will connect here itself, sir. Why you are writing another slide, sir?
No, I am drawing phasors. I cannot connect them like this.
Okay, sir.
I am drawing phasors. So B1, B2, and C will be here. C1, C2. So can someone, so this is definitely a Y, sorry, not Y, delta or D in the primary, Y in the secondary. Can someone tell me what will be the number here? Like we had YY0, YY6, what will be the number here? Can someone tell me? If you need to see the clock, I will just copy paste it once. This is the clock. So can someone tell me in what direction it will be? What should be the number?
12, sir. DY12.
Why 12? Your primary is here, while your secondary is pointing somewhere this side. So this is 120, this is vertical, so this is 90, this is 30. Looks like it's 7.
Okay, sir.
It's the A phase is looking towards 7. This kind of notation of, using the clock so as to show, using the clock direction so as to, clock notation so as to tell direction to people is also used in military. People use them in military notations also. Like if one soldier wants to tell other soldier to look behind, they will simply say, look at your 6. Or maybe they can say enemies on at 3. That means right side. So they will assume that they're looking towards 12, and in this way they communicate. 9 means left side. 2 means front right. This way. That is also used in normal life. Okay. And one more part that was there was open delta. I will shortly discuss on it. Shortly discuss about open delta. Okay. Open delta connection. I I will not go into details of it in the lectures. You will get to see everything about it. So open delta connections are used for very, sensitive loads. Sensitive load means the loads that you cannot stop a supply to. For example, a hospital. You cannot stop a supply to a hospital, or maybe some kind of industry. It is not done generally. That is not possible. So hospital, let us say, that is the most important example. So in hospital, what happens is you cannot stop the supply. There are many devices running which you stop operating, people might die instantly. So what is done in open delta connection? So you have, say, a delta transformer supplying to a hospital building. Now, if one of the transformers, say you can consider them, or not consider, you can imagine them as three single phase transformers. Out of them, one transformer develops fault. Reverse fault. So what will happen? In such a case, you cannot completely turn off the transformer, turn off the load, means supply, and then do repairment. Or for the time being, at least for some time, at least you have to keep the supply on for the emergency loads, say the incubators or other life-saving loads. So for such cases, what is this open delta connection becomes important. So normally what we have is, we have this kind of connection. Normally we have this kind of connection. So this is delta primary, which is getting supply from the high voltage transmission lines, and this is the secondary delta, which is supplying the hospital. So this is the connection, let us see. Now, say out of this winding develops a fault. This winding develops a fault. So what the engineers will do for the time being, they will quickly disconnect the corresponding secondary. As a result, what will happen is, you have, in the hospital, they will go and tell that this has happened to the transformer. What you have to do, you have to immediately turn off all the unnecessary loads. Turn off all the unnecessary loads. Unnecessary load means maybe the corridor illumination, maybe the TVs, screens for the relatives of the patients and such things. Unnecessary loads, they have to turn off, so that this transformer in open delta formation is still capable of supplying the load at a reduced level. Obviously, the emergency load they can supply. So what happens in this case is, you have your supply connected as usual, and this was going, the phase that was here, that is gone now, that is no longer there. So if you see the lecture, you will see. So let me give names. A1, A2. A2 means again B1, B2, which is again C1, C2. Now you see the supply voltage, that is still balanced, right? That has not been hampered. Supply voltage is still coming. So if you draw the phasor diagram of the remaining phases in the secondary I am drawing, you have A1, A2 here, and you have B1, B2. In this fashion, C1, C2 is not there, and the loads are connected. But if you calculate, say, I have voltage A1, A2, that is, say, 230 sine omega t, let us say. Say B1, B2 is 230 sine omega t minus 120. if you apply KVL here, you will see that C1, C2 will be nothing but minus of A1, A2 plus B1, B2, which is nothing but 230 sine omega t plus 120. So what we get out of it is, although one unit of the transformer or 1/3 of the whole transformer has been removed, the secondary side is still receiving a balanced supply. Secondary side is still receiving a balanced supply. Since the secondary side is still receiving a balanced supply, we can connect a balanced three-phase load. Three-phase balanced load to it, and the three-phase balanced load will see a three-phase balanced supply voltage, and it will draw a three-phase balanced current from it. So from the load point of view, nothing will change. Only thing is that the full load it cannot deliver. It will deliver the load at a lower level. So if you see the lecture, the level is 0.566, something close to this, of the actual load. So if the actual transformer could supply say 1 kVA, now it can supply 0.566 kVA if this open delta connection happens. Okay, and the phasors and all you can see there. I am not discussing. I have to discuss some problems if possible. It looks like from the time I can discuss only one, that's okay. You have your Tuesday doubt clearing classes also. There you can get your other doubts cleared. Okay. So this is a simple problem of a three-phase transformer connection. Read the question, okay. It says a 33 kV by 415 volt three-phase delta star transformer is feeding power to a 25 kilowatt 415 volt three-phase load with 90% efficiency and 0.9 power factor. We will look at the questions later, but later first try to understand the system. Okay. See, they are not talking about three single-phase transformers. The question is given for a three-phase transformer. Okay. A three-phase transformer which is rated as 33 kV by 415 volt. And it is a delta star connection. So what does it mean? See, when you are saying that I have a three-phase line of 33 kV, a three-phase is rated at 33 kV, that means the line-to-line voltage is 33 kV. Invariably, if not otherwise mentioned, line-to-line RMS is 33 kV. And it is connected in delta. So, if I draw the primary side of the transformer, it is like this, and the secondary side is star connected. Secondary side is like this. Okay. Now it is receiving this transformer is rated for 33 kV. So we will connect this transformer to a 33 kV line. So it is receiving supply from a 33 kV line. So the voltage between these two lines is 33 kV. So the line voltage here in the primary side, so I will write say V line primary is 33 kV. So can you tell me what is the phase voltage? So what is the voltage that is being experienced by each of these windings? Or in other words, what is the phase voltage in primary? Quickly. Delta connected primary side, line voltage 33 kV, what will be the phase voltage?
VL by root 3, sir.
VL by root 3? No, it will not be VL by root 3. See, this is delta. Just follow these lines. This is connected here, this is connected here. The same 33 kV is coming. The same 33 kV is coming. Phase
VL
voltage,
is to V phase, sir.
sorry,
VL is equal to V phase, sir.
yes, 33 kV. So when I have to connect this transformer in this 33 kV line, and all these windings, these three windings are rated
Sir,
for 33 kV.
sorry for disturbing you. Can you repeat again, sir? Sorry, I was not able to hear you properly.
Which part?
This particular sum.
Okay, so this problem says it's a 33 kV by 415 volt three-phase transformer, delta star connected, and it is feeding power to a 25 kilowatt 415 volt three-phase load with 90% efficiency. So for the time being, we are concentrating on this statement, 33 kV 415 volt three-phase delta star transformer. What exactly this thing means?
Okay.
So it is 33 kV. So blindly we can connect this primary to a 33 kV line.
Okay.
And since the secondary is 415 volt,
Yeah. Yeah.
when we are connecting this 33 kV, this transformer primary to a 33 kV line, say at no load, we are getting, no, these parts I am not repeating, I am telling for the first time.
Okay.
So I am getting 415 volt. Again, nothing is mentioned. So 415 volt is line voltage. So if I connect the transformer 33 kV primary side, then I will get 415 volt on the secondary side line voltage, right? So can you tell me, so what we have is V phase 2, secondary side is, sorry, not V phase 2, V line 2, secondary side is 415 volt. So can anyone tell me what will be the phase voltage?
Divided by root 2, no? 415.
No, not by root 2, by root 3.
Root 3. Okay.
So it will be this, 415 by root 3. Please, someone please do it and tell me the value. So all these windings in the secondary side, they are not rated for 415 volt. They are rated for 415 divided by root 3 volt. How much is it? Okay, I have to do
239.6.
239.6, yeah. 239.6 volt. So these windings are rated for 239.6 volt, whereas these windings are rated for 33 kV. So basically, if I
Yeah. Sorry. 33 kVA they have given as a phase voltage or how?
they have not mentioned anything. Only written 33 kV 415 volt three phases. So if nothing is mentioned, that is line voltage.
Okay. Okay. Okay.
So basically, if I want to realize this three-phase transformer with 3 units of single-phase transformer, I have to take single-phase transformers that are rated for 33 kV by 239.6 volt, right? Not by 33 kV by 415 volt transformers. I will end up getting over voltage on the secondary side. So I have to take 3 single phase transformers of this voltage rating, and then connect it in this fashion so as to get this rating. Or in other words, what I am trying to say is, what is the turns ratio? What is the turns ratio? The turns ratio is not equal to 33 kV by 415. The turns ratio is 33 kV by 239.6.
I'm not getting, sir, I'm not getting you this. Why? Because this is line voltage.
Yes.
The secondary is phase voltage.
No, secondary is also line voltage.
Okay.
Whenever
So,
it is three phase, it is line voltage. Yeah.
okay. Line voltage is 415. Secondary also 415.
Yes.
But we are not considering line voltage, we are considering phase voltage only divided by 3, divided by 239.6.
It's not that we are considering, it's that
Oh.
if I am getting 415 volt in the secondary line voltage, the phase voltage must be 239 volt.
Correct. But input is also line voltage, no? Then NY by
Yes, yes.
input is line voltage. So N1 by N2 should be line voltage only, no?
No.
From 330. Yeah.
N1 by N2 is turns ratio. How many turns I see? Let us look at these transformers. So basically, this is 1 unit of transformer. Say this. So when I have 33 kV induced, 33 kV applied in this winding, I am getting 239 volt induced in this secondary. That means if I count the number of turns here and here and make a ratio, I will get this 33 kV by 239. The turns ratio is in the transformer level. Say for example, this transformer.
Okay, got it. Got it.
Yeah. So say this transformer itself, if I disconnect all the connections here, all the connection I disconnect here and reconnect it so as to get us delta, then this transformer itself will become a 33 kV by 240 volt transformer. This will become a 33 kV to 240 volt transformer. Because 240 volt will, because the secondary will then become delta. For delta, phase voltage is same as line voltage. So it will become 33 kV 240 volt transformer. So my point here is when you have to find out the turns ratio for a three-phase transformer, you cannot simply do voltage by voltage. Turns ratio, you have to look at it from the transformer point of view, from every winding point of view. Okay. So that being said, we can now look at the question. The question says 25 kilowatt, 415 volt, three-phase load with 90% efficiency and 0.9 power factor. Okay, so what it looks like, since they have mentioned the efficiency of the load, so let us say it's an induction motor. Okay, so when you have a motor or something whose power is mentioned in this fashion, that means this is the output power. This is the output power. And it's 90% efficient. So the input power will be 25 kilowatt by 0.9. So the load, which is, let me write it down once again here, 25 kilowatt, what was the voltage? 415 volt, right? Yeah, 415 volt. That is the, so for 25 kilowatt is the output. So the input is 25 by 0.9. This much is the input power. So this much power is being drawn from the transformer secondary. So 25 by 0.9 will give me 27.78. 27.78 kilowatt of power is being drawn from the secondary. Now we know that three-phase power is given by root 3 V line RMS, I line RMS, cos phi. So what we have is 27.78 is equal to root 3. V line is 415 volt. I line we have to find out. Cos phi is given as 0.9. Okay, into 10 to the power 3. Can someone please do it and tell me? Okay, I can myself do it. 27.78 times 10 cube by root 3 into 415 times 0.9. Comes out to be 43 ampere. Say I line comes out around say 43 ampere. I'm not bothered much about the figures. Okay, we will try to understand how the things work. Okay. Anyway, now we look at the questions. The first question says, estimate the minimum required kVA of the transformer. The minimum required kVA of the transformer. So we have found out that 27.78 kilowatt is the active power, P. kilowatt is the active power that the transformer is supplying at a power factor of how much? 0.9. So now we have to find out Q. So what we have is, if S, we need not find out Q. Why do we need to find out Q? Is the active power is 0.9. So if S is the apparent power, S cos phi, oh, I was writing theta. I will write theta. S cos theta is P. So basically S is P by cos theta. So 27.78 by 0.9. 27.78 by 0.9 gives me 30.87.
30.86.
Yeah, 30.87. What is this? Kilovolt ampere. Kilovolt ampere. Apparent power. So this is the minimum required kVA rating of the transformer so that this load can be supplied. Okay. Now the question is, estimate the line current in the high voltage side. Okay, we have already seen that line current in the secondary side is 43 ampere. Okay, so 43 ampere is flowing here. Now, so 43 ampere, this is a star connected secondary side. So 43 ampere is also flowing in this, flowing here. Now, can you tell me what will be the current flowing here? RMS current. This current, say if I write phase current of primary, I phase 1. How to do? What should I multiply 43 with?
43 only, sir.
How can it be
Star
43?
I is what I face.
How can it be 43? Between this winding and this winding, there is a turns ratio. The turns ratio we just discussed. The turns ratio is 239.6 by 33. Okay. This much current will flow in the primary phase. So 43 times 2, tell me if you have a doubt. Quite less current, isn't it? Expected also. Expected also, because the primary voltage is very high compared to the secondary. I will try to get some things. Can I do? Okay. If you have a doubt, tell me. No doubt? Okay. So, the primary phase current is 0.3 ampere. Question is, what is the primary line current? What will the primary line current? IL1? Root 3 times 0.31 ampere. It is delta connected. Delta connected. So this current is nothing but you have to apply KCL here. Once you apply KCL, you will see magnitude wise, it will be root 3 times of this. So root 3 times 0.31, whatever it comes. So the basic point behind solving this problem in this much of depth is that you can no longer blindly apply the voltage ratios in voltages and current in three-phase transformer problems. You have to be very careful about the terms. You have to be very careful about the connection. See, the question says, estimate the line current. Estimate the line current in the high voltage side. Suppose the question did not mention line. Suppose the question had simply said estimate the current. Suppose this line is not there. Estimate the current in the high voltage side. What will you do? What would you do? Phase current or line current? It should be, yeah, anyone wants to say anything?
Line current, sir.
It should be line current. In three-phase system, if nothing is mentioned, voltage means line voltage, current means line current. Estimate the phase current in the high voltage side. We have seen. This line current thing we could have done from energy balance also. How much active power is going there, we have already found out. This much of kilowatt, and then again, Roche VLIL cost we could have done, but this is also a good thing. We can look into depth of the things. Phase current we have already found out. Line current in low voltage side we have already found out. Phase current we have also found out. Right? We have seen that line current is same as phase current. It is star connected. So the problem is done in this way. So the bottom line is, whenever you have problems like this on three-phase transformers, be very careful about the terms, about the connections. Better to draw a circuit in this fashion. Write the voltages, currents, so that you do not make a mistake. Because say when you are drawing the circuit, now you have it in front of your eyes that here I have a connection. So definitely this current. So let me take another. Definitely the current in this winding will be different from here. So there is a lesser chance of making mistakes. So do not simply jump and divide everything with this voltage ratio. This is deceptive. Especially if you have delta star or star delta kind of transformers. Okay, any doubt? If not, I will stop this session for today. No doubt, it seems. Okay, that's all. Thank you for joining. We'll again meet next Saturday. While before that, you have another, I thought I will discuss this, another doubt clearing class on Tuesday. Siva will take the doubt clearing class. You can join and clear your doubts if you have some more, if you get to watch some more videos.
Thank you, sir.
Yeah, thank you.
Sir, one small doubt,
Yeah.
sir. This is out of the subject. Actually, I'm not used to this NPTEL, previously, this is first time I'm doing. I am taking two courses. One is on control system. One is on this, particularly our machine one course. So I don't know where it